Okay, so let's get into it. There's this fundamental challenge with all the big language models we use today. They're incredibly smart, they're fluent, they have incredible capability.
Right.
But they don't have any inherent intent, not when they're first built.
Exactly. The pre-training goal is just next token prediction.
So it's just trying to guess the next word in a sentence.
Perfectly. And that gets you fluency, for sure. But it tells you nothing about, subjective qualities. Is it helpful? Is it safe? Does it have the right tone? It ignores all of that.
You get this massive, powerful engine with no steering wheel. So, for our deep dive today, we're looking at the system that builds that steering wheel. Reinforcement learning with human feedback. RLHF. Be like a black box. So today, we're going to try and cut through that abstraction. We're going to deconstruct algorithms right from first principles and hopefully reveal just how profoundly they underpin our world.
Absolutely. And at its heart, really, an algorithm is, it's a precise set of steps.
What?
Finite steps, step-by-step instructions, basically, designed to solve a very specific problem or, perform a task.
Like a recipe.
Exactly like a recipe. Think of it as the conceptual blueprint. It's the logical sequence, and it's totally abstract, language agnostic.
Yeah.
It's the pure idea behind the solution before it gets turned into code or anything runnable.
Right, the pure idea. And this blueprint thinking, it's not just for computers, is it? This precise sequential problem solving. It seems pretty fundamental to how we think, too.
Oh, completely. It has defining characteristics, right? Each step has to be unambiguous.
Right.
It needs to finish. That's the finiteness. It takes something in, an input, does something, and gives something back, an output.
And it needs to be general enough to work on different inputs, not just one specific case.
Yeah.
And effective, like actually doable.
Precisely. Think about tying your shoes. That sequence of steps, that's an algorithm. Or a navigation app, finding the best route. Algorithmic thinking is really a core human skill.
Okay, so here's where it gets really interesting for me. The relationship between that abstract algorithm, the idea, and an actual computer program. People often use those terms interchangeably.
They do, and it's a key distinction. The algorithm, again, is that abstract blueprint. The formula, totally language agnostic. A program, that's the concrete implementation. It's taking that algorithm and writing it in, say, Python or Java or C++ on.
Okay, so like the architect's drawing versus the actual house built from it.
Exactly that. The drawing has the logic, the structure. The house is the physical thing built using that logic. The program is where the algorithm lives and runs.
Got it. So how does that logic, that blueprint, actually tell the computer what to do? How does it direct the code?
Well, pretty much every algorithm, no matter how simple or complex, follows this universal pattern. Input, process, output, IPO. You give it data, that's the input.
Right.
It performs a set of instructions on that data. That's the process.
The steps.
The steps, exactly. And then it produces a result.
Simple enough. But how does it handle complexity, choices, repetition?
Well, that's where control flow comes in.
Yeah.
There are basically three fundamental structures. You've got sequential execution, just doing tasks one after another in order.
Okay.
The conditional logic, the if this, then do that, otherwise do something else. That lets it make decisions.
Makes sense.
And finally, iterative structures, loops. Repeating steps over and over, maybe until a condition is met. That's incredibly powerful for processing lots of data or refining results.
And that processing power, especially with iteration, must be why algorithms are so crucial in data science, right? With the sheer amount of data we have now.
Indispensable. Absolutely critical. Algorithms automate these incredibly complex processes on massive data sets, things humans just couldn't do manually, not at that scale or speed. They turn raw, messy data into actual, actionable insights. And they do it with high precision, consistency.
And they enable predictions, right?
Exactly. Predictive capabilities are huge. They let us see patterns, make forecasts. Without algorithms, big data is mostly just noise.
Can you give us some concrete examples? Where are they making a big difference in data science?
Sure. Think about predictive analytics. Forecasting sales for a business, or a bank assessing credit risk for a loan. That's algorithms at work. Or personalized recommendations, when your streaming service suggests a movie you might like.
Yeah, sometimes spookily accurate.
Right, that's algorithms analyzing your past behavior. Also, customer segmentation, grouping customers for targeted marketing, and critical stuff like real-time fraud detection in financial transactions.
Okay, that connects directly to machine learning then. It feels like algorithms aren't just tools for ML. There's something more fundamental.
They are absolutely the bedrock of machine learning, no question. ML at its core is about computers learning from data, finding patterns, and making predictions or decisions without being explicitly programmed for every single scenario. Algorithms provide the structure, the framework for that learning process. They enable the pattern recognition, the optimization like getting better over time, and the ability to generalize to new data.
So machines learn in different ways using different algorithmic structures. What does that landscape look like?
Broadly, there are three main types, three paradigms. First is supervised learning. Here, the algorithm is trained on data that's already labeled. You give it examples of inputs and the corresponding correct output.
Like teaching it, this email is spam, this one isn't.
Exactly. So it's used for classification, like spam filters, or regression, like predicting house prices based on features like size and location.
Okay, supervised. What else?
Second, unsupervised learning. Here, the data is unlabeled. The algorithm has to find patterns and structures on its own. Think clustering, grouping similar items together without being told what the group should be, like finding different segments of customers based purely on their purchasing habits.
Interesting. And the third?
Reinforcement learning. This one's different again. The algorithm learns by doing, by interacting with an environment. It tries actions, gets feedback in the form of rewards or penalties, and learns strategies to maximize its rewards over time.
Ah, like how AI learns to play complex games or how self-driving cars learn to navigate.
Precisely. Autonomous systems often rely heavily on reinforcement learning.
Wow, okay, so you've got supervised, unsupervised reinforcement, and presumably many specific algorithms within each. How does anyone choose the right one?
Yeah, that raises a really important question. The truth is, there's no single best algorithm. It's not like there's one magic bullet. The choice depends heavily on the specific problem. Are you classifying something? Predicting a value? Finding groups?
Right.
It also depends on your data. How much do you have? Is it ladled? Is it messy? And what do you need from the output? Just accuracy. Or do you need to understand why the algorithm made a certain decision? Interpretability.
So it's more art than science sometimes.
There's definitely an element of craft to it, yes. Understand the strengths, the weaknesses, the assumptions of each algorithm. It's often an iterative process. Try one, see how it does, maybe try another. The art of algorithmic craftsmanship, you could say. Okay,
so pulling this all together, algorithms are these fundamental, precise sets of instructions. They're beneath almost all computational problem solving today. They really are the logical architecture of our digital world, enabling all this amazing automation and prediction we see.
That's a great way to put it. And what's fascinating here, I think, as these algorithms become more and more woven into the fabric of society, making decisions in finance, healthcare, even justice, understanding their principles, how they work, what their limits are, where potential biases might creep in, that stops being just a technical issue. It really becomes an ethical imperative, doesn't it, for everyone? We need to ensure their use responsibly. Today, we're plunging into reinforcement learning, RL. It's this really fascinating area of machine learning. It's all about how agents learn to make sequential decisions basically through trial and error.
Exactly. And our mission for you in this deep dive is, well, to cut through the noise, unpack the core mechanics of RL, and clarify why it's such a game changer for problems demanding optimal decisions over time. You should get some real aha moments about how these systems learn from often quite delayed feedback.
Okay, let's unpack that. Our sources really stress that reinforcement learning is, at its heart, concerned with an agent making a sequence of decisions.
Yeah, in an environment that's dynamic, maybe uncertain.
Right, and the goal is always maximizing some kind of cumulative reward signal.
And what makes RL so potent, I think, is that unlike systems you train on static pre-labeled data sets.
Like in supervised learning.
Precisely. RL actively discovers the best behavior through continuous interaction, trial and error. It's really uniquely suited for that sequential decision-making where the impact of an action isn't always immediately obvious.
Let's try and ground this. The classic analogy is training a dog, right? Dog's the agent, the living room is the environment. Actions like sit, get a reward, maybe a treat. But, for our deep dive, let's maybe pivot instantly to something more complex.
Yeah.
Think about an autonomous drone navigating a forest.
Okay, yeah.
Here, the state isn't just dogs sitting by the door. It's like this high-dimensional input of LiDAR data, GPS, camera feeds, much more complex.
That interactive loop, though, that defines RL, you always have these 5 core components.
Yeah.
the agent that's the decision maker,
Got it.
the environment, the external world it interacts with, the state that's its current perception of the world, like that drone's sensor data,
Right.
the action, what the agent chooses to do, and the reward, which is that immediate numerical feedback, good or bad.
Okay, so those are the building blocks. Agent, environment, state, action, reward. But how does it actually decide what action to take in a given state? That gets us to the policy, right?
Exactly. The policy is essentially the agent's master strategy. Think of it as a map from states to actions.
A map, okay.
And policies can be deterministic, like always do this action in this state, or they can be stochastic.
Stochastic. So probabilistic.
Yeah, providing a probability distribution over actions. Deterministic is fine if the world is perfectly predictable.
But it rarely is.
Right. So stochastic policies are vital. They help with exploration, trying new things, and they're crucial in, say, adversarial settings like poker. If you're too predictable, you get exploited.
Okay, that makes sense. You need some randomness.
A bit, yeah, to learn robustly.
So building on that policy idea,
Yeah.
if a reward is like a single paycheck you get right now, then the value function sounds like it's more about the long game, like a financial forecast for the next decade, the total expected reward down the line.
That's a great way to put it. It's this forward-looking perspective. It's often formalized by something called the Bellman equation, which is, well, it's really the backbone of many RL algorithms.
Why is it so central?
Because it lets us break down this huge, complex, long-term optimization problem into smaller, recursive steps. It essentially says the best value of being in a state now is the immediate reward you get, plus the discounted best value of whatever state you end up in next.
Discounted, meaning future rewards are worth a bit less than immediate ones.
Exactly. It encourages prioritizing achieving goals sooner rather than later, and it also keeps the math as manageable. It helps the agent weigh long-term gains against short-term ones.
So as the agent is learning, refining his policy, figuring out these values, it hits this classic problem, right? The exploration-exploitation dilemma.
Ah, yes. The ultimate dilemma, isn't it? It's like finding a restaurant you absolutely love.
Yeah.
Do you just keep going back, exploiting that knowledge? Or do you explore that new place across town that might be even better but could also be terrible?
Right. The risk versus the known reward.
Precisely. That balancing act. Exploiting what you know works versus exploring new possibilities for potentially much bigger payoffs. Getting that balance right is absolutely core to learning optimally in RL. Too much of either isn't good.
Okay, that provides a really good picture of the mechanics inside RL. But, stepping back, we already have supervised learning, unsupervised learning. What is it fundamentally that makes RL stand out? What problems can it solve that the others can't really touch?
The key differentiator, I'd say, is the credit assignment problem.
Credit assignment. Explain that.
Okay. In supervised learning, the feedback is instant. You show it a cat picture, it says dog, you immediately say, no, that's a cat. The feedback is right there, tied to that specific input.
Got it. Direct link.
But in RL, imagine playing chess. You make a brilliant move on turn 10, but you might not actually win the game until turn 50. The profound challenge is figuring out which of the many actions you took before that win were actually responsible for it. Was it that move on turn 10, or something on turn 35, or a combination? Assigning credit back in time to the right actions. That's tough.
Because the reward is so delayed.
Exactly. And this is precisely why techniques like Q-learning and temporal difference learning, or TD learning, are so fundamental in RL. They give us elegant ways to propagate that delayed reward signal back through the sequence of states and actions, even if we don't have a perfect model of how the environment works.
Oh, it's like learning a really complex skill.
Sequential delayed feedback and the algorithms designed to handle it, that's what truly makes RL unique.
And we see this playing out spectacularly in video games, right? They become this amazing sandbox for RL.
Oh, absolutely. I mean, from classic Atari games like Miss Pac-Man's simple actions, but millions of possible game states all the way up to DeepMind's AlphaGo Mastering Go.
Which has an astronomical number of states.
Astronomical. And OpenAI's Dota 2 AI. These RL agents learn strategies that are often at or even beyond human level. They frequently use deep neural networks now to handle the sheer complexity, approximating those policy and value functions by basically playing millions and millions of simulated games.
You mentioned something earlier about intentional imperfection in commercial games. That sounds counterintuitive. Isn't RL all about finding the optimal strategy? Does needing imperfection mean RL has limits? Or is it something else?
That's a really sharp question. It's less about a limitation in RL's ability to find the mathematically optimal path, and more a challenge in defining what optimal means when humans are involved. An AI that finds some obscure loophole to win every single time might be optimal according to its reward function, but it would be incredibly boring or frustrating for a human player.
Right, ruins the fun.
Exactly. So it's more an adaptation. Game designers carefully shape the reward signals, or sometimes they combine the learned RL behaviors with more predictable scripted actions. The goal shifts from pure mathematical optimality to creating an opponent that's engaging, challenging, maybe even feels fair, even if it's not technically playing perfectly. It reflects that the goal is often more nuanced than just winning.
That makes a lot of sense. So wrapping up then, reinforcement learning gives us this distinct, really powerful way for agents to learn the best policies just through interacting with their world.
And brilliantly balancing that need to explore new things with exploiting what already works, all to maximize that cumulative reward over the long haul.
And it's clever ways of tackling that credit assignment problem, handling delayed rewards, and adapting on the fly.
Yeah, it means the applications are just exploding well beyond games. We're seeing it increasingly in robotics, personalized medicine, complex financial modeling, sophisticated recommendation systems. It's really versatile.
We have covered a lot today. So next time you see an AI making what looks like smart sequential decisions, maybe pause and consider that intricate dance. It's doing actions, states, rewards, exploration, exploitation, constantly learning.
It really is a fascinating process. Reinforcement learning with human feedback. RLHF.
Right, RLHF is the bridge. It's how you take raw capability and align it with human preference.
How does that actually work? I imagine it's not a single step.
No, it's a pipeline. You can think of it in about 3 stages. The first one is basically just teaching the model how to speak properly in context. It's called supervised fine-tuning, or SFT.
SFT.
You take that huge pre-trained model and you show it a much smaller, really high-quality data set of like ideal conversations. Here's a prompt. Here's the perfect response.
So you're giving it a good example to follow.
You're giving it baseline, a starting point. We call it the SFT policy, and it becomes the anchor for everything that comes next.
That gets you a model that can follow instructions. But what about that gray area, that, subjective goodness?
Yeah.
How do you even assign a number to taste?
Yeah, and that's why standard reinforcement learning just fails here. The reward signal is way too complex. So RLHF's really clever solution is stage 2, teaching it taste.
And how do you do that?
With a completely separate model, a reward model. We don't try to define the perfect answer ourselves. We just have human labelers look at 2 different answers, A and B, and say, I prefer A.
So it's just a simple comparison.
A simple comparison. That ranking data is then used to train the reward model, and its only job is to learn what humans prefer. It turns that subjective choice into a consistent mathematical score.
I see. So the LLM isn't grading itself. It's learning from a different model that acts as a proxy for human preference.
Precisely. And that score becomes the reward signal.
Which brings us to stage 3. This is where you actually use that reward to steer the model.
Right. This is where we bring in the RL part of RLHF. We use an algorithm called proximal policy optimization, PPO, to fine-tune the LLM, trying to get it to maximize that score from the reward model.
Okay, so it's just chasing a high score.
But here's the catch. If you let it just chase the reward, it starts producing gibberish. It forgets all its language skills because it's so focused on pleasing the reward model. We call it policy drift.
It becomes unhinged.
It does. And this is where it gets really interesting. To stop that from happening, you add a constraint, a penalty. It's called the Kale divergence penalty.
Ah, the secret sauce.
That's the one. It's basically a mathematical tether. It forces the model to stay close to that original SFT baseline we created in stage 1.
So it's a tug of war. The reward model is yelling, get a higher score. And the KL penalty is pulling back, saying, yeah, but you still have to sound like you know how to speak English.
That's a perfect way to put it. But that whole PPO process, it's just brutally complex. You're juggling 4 different large models at once to make it work. The main model, the reference model, the reward model, and another one called a critic.
Wow, that sounds inefficient, like a massive computational headache.
It is, which led researchers to look for a shortcut. And they found one, which is now incredibly popular. Direct preference optimization, or DPO.
DPO, so it's a simpler path to the same goal.
Much simpler. It turns out there's a clean analytical solution to that exact Kale-constrained objective.
An analytical solution, meaning you don't need to train a separate reward model anymore.
You don't. You can get rid of it entirely. DPO essentially lets you optimize the policy directly on the preference data, just using a simple loss function. It bakes the reward calculation right into the process.
So you go from that four-model mess down to something much more like a standard supervised training run.
Exactly. It's more stable, way cheaper computationally, and often gives you better results.
So tying this all together for you, the listener, what this means is that alignment is this constant balancing act. You're trying to maximize a score based on human taste, but you always have to be anchored back to fundamental language fluency.
Right. And for all this control, there's still a lingering risk. It's called reward hacking.
The model finds a loophole.
It finds a loophole. Because the reward model is just a proxy for what we actually want, the LLM might find clever, unintended ways to get a high score without actually being useful. It's a classic example of Goodhart's law. It shows that alignment isn't something you solve once. It's an ongoing process that needs constant, careful feedback.